Section 8.8 deals with improper integrals. Now in this section, what we're going to do is look at integrals that have one of the following problems. Their domain is infinite, and what that means is that one of the limits of integration is positive or negative infinity. Or their range is infinite, and what that means is that within the limits of integration, they have a vertical asymptote. So there'll be a vertical asymptote at or between the limits of integration. And that is similar to the one that we looked at in section 5.6. Again, if you look at this function and were to just graph that function, 1 over x, well, it looks like this. Notice from -1 to 1, it is unbounded. Since it's unbounded, you have a problem when you're trying to find the area under a curve. If we look at a graphical representation of infinite domain, we'll notice it's the same function we graphed when the range was infinite, but we're only going to graph the right-hand side since I'm going from 2 to infinity. And so basically it's, if I've never stopped going, am I going to approach a finite value? Can I find the net area under the curve? Those are our two problems, infinite domain or infinite range, and let's look at how to solve these improper integrals. The first type we're going to look at are the ones that are involving that plus or minus infinity, the limit of integration either being positive or negative infinity, which means the infinite domain. Within that, 3 different scenarios can occur, and let's look at those 3 different scenarios. In the first scenario, your upper limit of integration is infinity. So if your function is continuous from a to infinity, then what happens is you need to rewrite this definite integral as a limit statement, replacing infinity with a letter, in this case c. Then, once you rewrite it as a limit statement, you will evaluate your definite integral as you normally would, and then once you have your answer, you evaluate the limit at that answer. So you're going to rewrite the integral from a to infinity of f of x dx as the limit as c goes to infinity of the integral from a to c of f of x dx. Again, find the value of this definite integral and then evaluate that at the limit as c goes to infinity. If your lower limit of integration is negative infinity, it's the same thing. Your function is going to be continuous from negative infinity to b, and you're going to replace that negative infinity with a letter. In this case, you're going to say the limit as c goes to negative infinity of the integral from c to b of f of x dx. And then all you're going to do is evaluate this guy right here, this definite integral, at those limits of integration, and then evaluate the limit as c goes to negative infinity of that answer. The third one is just if you have upper and lower limits of integration that are infinite. So you have negative infinity to positive infinity. Therefore, you're looking at something like the integral from negative infinity to positive infinity of f of x dx. What you do in this case is you choose a number, any number your heart desires, between negative infinity and positive infinity. Typically we choose 0 because 0 is an easy number to work with, but if your favorite number is 10, you can choose 10. It doesn't matter which number you choose. But you split yourself up into 2 separate integrals. Well, notice this guy right here looks just like letter B, and this guy right here looks just like letter A. Really, what happens is if you're going from negative infinity to positive infinity, if those limits of integration are from negative infinity to positive infinity, you split yourself up into 2 separate limit statements. The first one, the limit as a goes to negative infinity of the integral from a to c of f of x dx, plus the second one, the limit as b goes to infinity of the integral from c to b of f of x dx. So you're still splitting yourself up over whatever number you chose. Remember, typically we choose 0, but then again you have to get rid of negative infinity and make it into a limit statement. And you have to get rid of positive infinity and make it into a limit statement. Now, as I said before, what's going to happen is you rewrite your improper integral as a limit statement. Then you evaluate your definite integral. Once you evaluate your definite integral, then you're going to evaluate that answer at the limit. If, when you're doing that, your limit exists, then what that means is that your improper integral converges, and the limit is the value of the improper integral. So if your limit was approaching 105, then the value of the improper integral is 105. You can think of it as the definite integral was approaching 105. But if the limit does not exist, so if your limit does not exist, things like you're ending up with positive or negative infinity, because we know that when we end up with positive or negative infinity, that means our limit didn't exist. It was just describing the behavior of the graph. Or if you just end up with something that does not exist, then what happens is the improper integral diverges. If you're imagining it as area under the curve, basically think of it as the area under the curve never approaches a number. It's getting infinitely bigger or infinitely smaller. Let's look at the first two examples where we are going to determine whether the improper integral diverges or converges, and then evaluate the integral if it converges. First thing that we do is rewrite it as a limit statement. I notice here that I have infinity as an upper limit of integration. So I have to rewrite it as a limit statement. I'm going to say this is equal to the limit as c goes to infinity of the integral from 1 to c. So instead of writing infinity, I write c. And then 1 over x squared, if I'm going to find its antiderivative, it's probably better to write it with a negative exponent. So let's say x to the negative second dx. Now integrate. Limit as c goes to infinity of, if I integrate x to the negative second dx, I get x to the negative first over negative 1, and that gets evaluated from 1 to c. Clean it up and then plug in the limits of integration. The limit as c goes to infinity of, this becomes negative 1 over x, evaluated from 1 to c. Now let's plug in those limits of integration. The limit as c goes to infinity of, this becomes negative 1 over c, minus, but minus a negative becomes a plus, and then this is 1 over 1. Now, remember what I said is that the first thing you're going to do is evaluate the definite integral. So here we go. We have evaluated the definite integral. Once you evaluate the definite integral, then you take the limit as, in this case, c approaches infinity of your answer. And now you're going to determine if your improper integral diverges or converges. It'll converge if this limit exists, and it'll diverge if this limit does not exist. Let's figure out what happens when you're putting in infinity. Well, this is really a negative 1 over infinity plus a 1 over 1. Well, negative 1 over infinity, remember when you had a constant over a variable to a power, this guy here is just equal to 0. And 0 plus 1 is 1. That means that my limit exists, and since my limit exists, my integral converges. So in this case, my integral converges because the limit as c goes to infinity of negative 1 over c plus 1 over 1 is equal to 1. Let's look at number 2, the integral from 1 to infinity of 1 over x dx. The first thing you do is you rewrite it as a limit statement. Instead of infinity, I write the limit as c goes to infinity of the integral from 1 to c of 1 over x dx. And I'm going to leave it as a 1 over x dx because it's basic form as it is. We know that that's equal to the limit as c goes to infinity of the natural log of the outside value of x, evaluated from 1 to c. We plug in our limits of integration. The limit as c goes to infinity of the natural log of the outside value of c minus the natural log of the outside value of 1. Now we evaluate the limit statement because we're done with evaluating the definite integral. Now evaluate the limit statement. So what is the limit as c goes to infinity of the natural log of the outside value of c? Well, if you're not sure, just look at the graph. What is the natural log of the outside value of c? So in this case, we're going to say the natural log. For absolute value, you hit math, and then you scroll 1 over to number, and then hit enter for absolute value. And we don't need it to be c, we can just say x. If I'm just trying to figure out what does the natural log of the outside value of x look like, and we look at a graph, notice that as we are approaching infinity, so as c goes to infinity, this guy's increasing without bound, so I know that this here is equal to infinity. We also know that the natural log of 1 is equal to 0, so that's just 0. And infinity minus 0 is just infinity. Now what this means, when we're equal to infinity, this means that the limit does not exist. Recall that when we're equal to positive or negative infinity, when we take the limit, all that means is that the limit doesn't exist and we are describing the behavior of the graph. Therefore, since my limit doesn't exist, I get to say that my improper integral diverges. There's a theorem that deals with the integral from 1 to infinity of dx over x to the p. If you have the integral from 1 to infinity of dx over x to a power, what we say is if p is greater than 1, your improper integral converges, and then the value of the limit, or the value of the improper integral, is that 1 over p minus 1. And if p is less than or equal to 1, then your improper integral is just going to diverge. We'll look at examples 1 and 2 that we were looking at earlier. Notice that this is a 1 over x dx, so if you think about it as a dx over x, here your p, or your power on x, is 1. When p is less than or equal to 1, we automatically know that our integral diverges. That's exactly what we got. For number 1, if we think of this as dx over x squared, our p here would equal 2. Well, 2 is a number that is greater than 1, therefore we know we are going to converge, and then this answer should be 1 over p minus 1, in this case 1 over 2 minus 1, or 1, which is exactly what we got. Now this shortcut works if you're looking at integrals in this format. Since not all the integrals are in this format, we won't always use this theorem. But if you have an integral that is in this format, I encourage you to just use this theorem to find out if your integral converges or diverges.